Hello all of you. So in the last few lectures we have been discussing the lattice model of solutions. So in today's lecture we will critically review that lattice model and try to find its shortcomings, and going further I will discuss the theoretical basis of molecular simulations and how molecular simulations can address those shortcomings of lattice model. So just to quickly recap on what we have been doing, so we had assumed that we are discussing a system of solute and solvent, that is a solution, and they cannot just be anywhere in space, but they are occupying sites on a lattice. So each of these sites are occupied by a solvent or a solute. So there are some problems with that model, but before that let us try to see what is the big advantage of the model. So first of all, the model is clearly very simple. We can analytically solve it, and what we were able to show is that I can derive the expression of f of phi or f of phi t, but temperature we have replaced by the variable chi, and using that we then have a expression for the phase behavior. We can characterize the mixing and all that. So if you have looked at it carefully, the only variable that is kind of not known a priori is the variable chi. Of course, we know the expression of chi, that is minus z delta epsilon 2 kBt, where z is the coordination number of the lattice. For square lattice it is going to be 4 in 2 dimensions. In cubic lattice it is going to be 6. We can think of any kind of a lattice that will have a different coordination number. But clearly, since the original idea was that the solute and solvent is occupying the continuous space, there was no lattice in reality, it was only an assumption. This z happens to be in some sense model dependent. In fact, we can think of the continuous space as the limit when z is going to infinity, because molecules can be anywhere, right. So if that is true, then we are doing the actual system, but you may imagine that as z increases, the complexity somewhat increases and all that, right. So clearly we have more number of sites, and that if I am analytically solving it, it is not really a problem, but as we have discussed, even there we had made many assumptions, and if we try to numerically solve it without those assumptions, then it is clearly going to be difficult as the number of sites become huge. Delta epsilon in some sense is still model dependent, because we have assumed that at any particular site you have interactions only between the nearest neighbors, but nonetheless delta epsilon included the solute solvent and solvent interactions, minus 2 epsilon ps solute solvent, epsilon ss is solvent, and epsilon pp is solute. So clearly this delta epsilon has to be determined somehow, and we will look at in more detail in a minute. But before that, let us say that I know the phase behavior from an experiment for a particular system of solute and solvent, or a particular liquid solution. If I know the phase behavior, I expect that at the qualitative level, the behavior is going to be the same as we have obtained in the lattice model. If that is not true, then the lattice model is not a good representation of the system in the first place. So whatever assumptions that we have made in the model, it should be such that at least the qualitative features are captured of the phase behavior, right. So, if we have an experimental data available, then I can therefore fit my lattice model, the results of lattice model, and using that I can then find the value of chi, right. So, chi in principle can be determined from experiment, and this is not really something I would say so bad. As a chemical engineers, that is what we are used to doing, right. So, most of the models that we are used to see, they always have some model parameters, and the model parameters of course come from experiments. Let us say if I look at the pressure drop in a pipeline, we need to know the viscosity, and viscosity has to be coming from the experiments typically. Of course, we can get that from molecular simulations as well, we can get to that later, but in most cases we do an experiment and can find that particular parameter. The simplicity of the model is such that there is only one fitting parameter, that is chi, and therefore, it is quite natural that the model will have wide applicability even without worrying about the fact that chi is indeed a fitting parameter. There are tables for many systems where the experimental data has been used to find the chi values. So, if I want to look for any experimental system, in most cases there are ways to estimate chi, or there are already literature data on the values of chi that has been obtained by fitting some kind of experimental data. Particularly in the literature of polymer solutions, this has been the practice since very long time. So, that is, I would say, the advantage part of it. Now, let us look at the disadvantage part of it, and that really comes from the assumptions that we have made in the lattice model. So, disadvantage really is from the assumption that we have made. So, the first assumption that we made was a mean field assumption or mean field approximation, and that says that I did not consider all possible configurations, means I did for the perspective of entropy, but I did not consider in the perspective of energy. I assumed that the energy of all the configurations, I mean different arrangements of solute and solvent are the same, and that is equal to the mean energy. That is to say that my EI is equal to some average value E bar, and we estimated that, and then basically we looked at the number of contacts in an average sense, and that is how we got the E bar value. And once we have that, we can get the partition function. In the entropy component of it, we did account for the number of configurations, but energetically we assumed that all the configurations have the same energy. So, clearly this means that we do not have the effect of fluctuations in the model. So, any property that is expected to vary with energy fluctuations, such as specific heat for example, is not being captured. That is the assumption in the model. As long as the fluctuations are not so important for what we are interested in, it is fine, but nonetheless it is a problem, I would say, even in those cases, because the accuracy will not be appropriate. But in the cases where the fluctuations are important for the description of property, in that case clearly the mean field will fail. The second assumption that we made, and not in the particular order that I described, but the second assumption we made was that Vp, that is the volume of the solute, is equal to the Vp, the volume of the solvent, and this is then equal to the volume of the site or the cell, and this is then equal to a constant. And if you think about it, the last bit of it is coming from incompressibility, and the first bit is coming from the fact that we are assuming that the solute and solvent occupy the same volume. So, we are basically disregarding the molecular structure of solute and solvent. Therefore, the model is quite general. We are not differentiating between, say, an ethanol molecule and a water molecule. Clearly, ethanol will be expected to be much larger in volume than compared to water. For the case of polymer solution, we said that we can divide the polymer into various small units which will have the same volume as a solvent. So, there are ways to account for that in some sense, but it is still going to be not very accurate, right. We can also think of models which will have different sites for the solute and solvent, but you can imagine that that model will be going to be complicated, right. So, therefore, these can be accounted for, but that is going to be complicated, right. The whole idea why we started doing the lattice model was that the inherent simplicity, we can get analytical solutions in the limit of mean field. If that is not happening, probably the lattice model is not so much worth doing, because anyway it is a TOI model. The third assumption that we are making is that the chi is kind of given to us, and I was just telling you that that means that we have some kind of experimental data, we are doing some kind of fitting exercise to get the value of chi, or someone else has found it using whatever method that they are doing. In the model itself, we do not have a way to find the chi value. The final assumption in the lattice model, actually the first one when I was describing it, is that we are working on a reduced phase space. So, particles can only occupy lattice site, and I can put the second term separately, that the fact that the momenta value of particles can be different has not been accounted for. In fact, we haven't mentioned the momentum anywhere in the development of the model, because what we have been looking at was only the configurational part of the partition function. We are not looking at the distribution of momenta. I said that we can factor out that contribution from momenta, but I did not tell you like how to do that. At least it is not inherent in the lattice model. So, therefore, we are doing a reduced phase space. Now, let us try to address these limitations one by one. So, the first one, we have a mean field approximation, and we said that my EI is equal to E bar. If you think about it, that need not have been assumed, because inherent in the model is the fact that we have some epsilon interaction between different species, epsilon pp, epsilon ps, epsilon ss, right. So, within the lattice model framework, if I know the configuration, I can find the energy value, and clearly that energy value will be different for different states. The only difficulty then would be that if I want to address this, then we will have to go for numerical solution, because the simplicity is kind of lost there. In this particular case, we were able to write our partition function as something like that. That is not going to be possible in this case. We really have to sum over the various possible configurations, and that is clearly going to be more complicated, and you may imagine that we will need a numerical solution. So, within the context of the lattice model, still we have a way to find the EI value, but that will not give me as simple solution that we have got within the mean field approximation. But that is not really the main concern, as we can discuss. The next concern is right here. I was telling you that this can be accounted for by doing a more complicated lattice. This part in fact is, even though there can be liquids which are not incompressible, I mean, if I want to put it correctly, all the liquids will be compressible, but the amount of the compressibility will vary, right. So, gases of course are highly compressible, the liquids are less compressible. That means the density changes in the gas with, for example, temperature are going to be quite significant, but it is going to be quite small for the case of liquids, and so is true with pressure and so on, right. So, that is not really a big concern, so as to speak, as long as we are looking at a liquid. If I want to simulate a gas, then yes, then of course we have to be concerned. If I want to, for example, look at the transition from a gas state to a liquid state, that means we are looking at some kind of a phase transition, then this is a concern and this has to be accounted for. That also we can think that we can do, because I assumed that my every site on the lattice is being occupied by the solute or solvent. That need not have been assumed. We can assume that some sites are empty, kind of vacuum between the two molecules, right. That is still a possibility, even if we want to consider a gas within the context of a lattice model. That is also not a big concern. The last two are the ones which should be of great concern to us. First of all, we are doing on a much reduced phase space. So, clearly we are not sampling all the possibilities. By constraining the particles to the lattice site, we have really made a big assumption in terms of the entire physics by which the particles are moving, right. And the so is true for the value of chi, because first of all I have assumed that the interactions are only between the neighboring particles. That also in some sense we can relax by assuming that I will consider interactions between the next nearest neighbors and so on, but it is going to be complicated, right, in the context of lattice model. But even then, even if I assume interaction with the next nearest neighbors, or let us say all the molecules or particles in the lattice, even then the fact that the particles are constrained would mean that my interactions are not being captured well, and clearly the momenta are not being accounted for. So, let us try to argue that all this can be addressed when I am doing a molecular simulation, and of course, that is going to set the ground for what I will discuss in the next week, that is the Monte Carlo simulation, and the following weeks when we discuss the molecular dynamics simulations. So, I want to return to the picture of the phase space. I said that the Hamiltonian that represents the energy of the system has two components, the kinetic energy and potential energy. I can write the kinetic energy as sum over all the particles in the system momentum squared by twice their masses, and I can write the potential energy as some function of the coordinates r I. So, therefore, we can imagine that we have a phase space formed by these momentum values and these coordinates, right. By the way, when I talk about coordinates, although I always tend to draw a Cartesian kind of coordinates or Cartesian kind of plots, it does not really matter if I work in cylindrical coordinate or spherical coordinate. In general, we can replace this with something like a generalized coordinates qi, and by the way all of them are vectors, which would then be in any coordinate system we are working with. And the reason why we could do that is because different coordinate systems are related by coordinate transformation, right. So, yes, the Ri values and the Qi values, let us say if I compare the Cartesian and cylindrical coordinates would be different, but they are related still by some kind of coordinate transformation, right. So, I can always write the coordinates in any coordinate system as a function of the coordinates in the Cartesian system by some sort of a coordinate transformation. So, let me therefore represent the phase space in general as something like the momenta and the generalized coordinates. So, h is going to be a function of these variables, and how many are there? So, for n particles we have n momenta value and n coordinate values. Now, each of the individual momentum, that is momentum of every particle, will have 3 components in 3-dimensional space. So, in total we will have 3 n momenta in the 3-dimensional space and 3 n coordinate in that give me 6 n variables. We can also call them as dimensions, because the Hamiltonian depends on the 6 n variables, right. So, you may imagine that is a function of 6 n variables, and I want to plot this function, right. So, for 1 or 2 variable it is still very intuitive to plot. Let us say for example, we have a function that is a function of x and y. So, let us say there is some function of x and y. How will I represent that? So, I can plot f of x y on one axis and x and y on the other 2 axes, and this function is then going to be some surface in this plot, in this 3-dimensional plot. Now, you may imagine that that function is a function of 6 n variable. So, how many dimensions we need? We need 6 n dimensions, and clearly beyond 3 dimensions I can no longer plot on board. So, therefore, it is important to develop some kind of a representation of that 6 n dimensional space, and let us try that. So, what I would then say is I would represent the momenta along the so called y axis and the coordinates along the so called x axis, but then this is some sort of a representation of 3 n variables, and this is a representation of 3 n variables. So, we should not think of it as a 2D plot as it looks like on board. We are simply drawing a 2D plot because we cannot draw a 6 n dimensional plot, right. Nonetheless, if I look at any point on this particular plot, that would correspond to a particular value of the momenta and the coordinates, right. So, a set of coordinates and set of momenta will give rise to a unique point on this 2D plot, or a unique point in the 6 n dimensional space, right. Just like a point on this plot give me a unique value of x and y. So, therefore, if I have to represent the phase space, this is one way of doing it, and always keep in mind that this is no longer a 2D plot that we are used to, but nonetheless every point on the plot represents a unique value of the set of momenta and a set of generalized coordinates. And this point is what I would then represent as some tau gamma, and I would say it is a phase point. So, therefore, a phase space is actually a space of these phase points, which are every point is a set of the generalized coordinates and a set of momentum value, right. So, now if I go back to the idea of ensembles that I have been discussing, you will note that every micro state in any of the ensemble that we discussed corresponded to a given set of momentum and a given set of coordinates, right. So, every microstate has a unique value of the momenta and the coordinates. I mean the entire set is unique, right. So, individual momenta can be same between the two microstates, but the entire set of the momenta and generalized coordinates will be unique for a given state. So, therefore, this phase space in some sense is representing the micro states of the system. So, if I look at the system, so if I look at any molecular system at any given time, I may have a particular value of the momenta and the coordinates, and that will correspond to a point on this particular plot I have drawn. That will be a phase point gamma. So, gamma will represent state of the system at any given time, and that will clearly change with time. So, if I take a picture at say 10 different times or at 10 different locations, I will get different values of gamma, because the coordinates and momenta are changing way too often than we can imagine, because we are dealing with molecular systems. They are experiencing collisions, the molecules are moving and so on and so forth. So, the gamma is really a dynamic variable that keeps on evolving as a function of time and as a function of space, so as to speak. So, then what we can then say is, if I start looking at any of the system from at any particular time, at any particular location or whatever, I am always starting with some particular value of gamma, and then this gamma is changing with time, right. So, you will have some sort of a trajectory starting from a given phase point, and we can call the trajectory some gamma as a function of t. So, now if I start with some other state, let us say if I start from here, I will have some other trajectory, right. But nonetheless, the key point here is that if I can study all possible trajectories of all starting from all possible states of the system. So, going back to the idea of ensemble, we said that we have some A states, and A is really a large number. You can imagine that A is almost infinite, right. But if we can, hypothetically speaking, if we can start from each of those states, and if I can run some kind of a simulation for very long time, and that simulations, if it captures the gamma t as it evolves, we will therefore have a clear representation of the system dynamics. And since my Hamiltonian is a function of this P and Q, so I am writing in a compact notation now, because P is the set of Pi and Q is this set of Qi. So, always keep in mind that this P and Q are 3n variables each, right. So, if I know the P and Q value, I know the Hamiltonian. So, I know the energy of the system, and if you recall, that is all that goes in our thermodynamic apparatus of the ensembles and so on, because once I know this, then I am pretty much done, because I can then figure out the energy in different states, and using the energy value I can then find the average energy. I can define the partition function. Depending on the ensemble, you will have different partition functions, and then once we have that, then we can find the properties of interest, right. So, in the end, I'll do that hypothetical picture that I was telling you of counting all the trajectories looks to be very difficult to do or almost impossible to do. If we are able to do that, then we will have the complete thermodynamics of the system that we are considering, right. And it turns out that even though that particular thing that I mentioned is not quite possible of starting from every possible state and looking at the trajectories, what is indeed possible is I can look at one of these trajectories. Let us say if I focus on this guy, I can do this for a reasonable amount of time. This is what we do in a molecular dynamics simulation, that is an MD simulation, right. So, even though we cannot do starting from all possible state, for one possible state for a finite amount of time, we can clearly do that. I mean, that is the capability that computers currently have. And of course, whenever I say that, I am also saying for a finite small value of n. So, for finite small time, for finite small value of time, we can simulate this starting from one particular state. Now, the question then is that starting from that particular information of trajectory that has started from one of those states, or that information of one of the trajectory out of all possible trajectories, what we can then infer, because even in this situation we are not in a sense capturing the entire phase space. So, the reason why we set out doing this was because the lattice model was not capturing the phase space. But even after doing this, we have showed that yes, we can do MD, but since there are too many states and infinitely many states, doing all of them is not possible. So, at least one of them for a given amount of time I can do. So, is that any better than the lattice model? And the answer is yes. And the reason gets into because not only we can do that, but we can also account for the interactions in a much better sense while doing that. It is not like a lattice model where I had assumed that there is interaction between only neighboring particles. We can account for interactions in a more general sense in this particular framework. So, I would like to stop here. In the next lecture, we will discuss I would say a very basic framework of molecular dynamic simulations, and then I will try to compare with a basic framework of the Monte Carlo simulations. And in the following weeks, we will first discuss the Monte Carlo simulation in more detail, because that is somewhat simpler to think about, and after that we will discuss the molecular dynamic simulations. So, with that I want to conclude here. Thank you.